Hey guys, in this video we will be exploring Graph Attention Network. First, the data that we use for this notebook is the Cora graph dataset. This is a node classification dataset with 2,708 nodes, about 10,000 each. The node feature dimension is 1,433. The nodes are classified into 7 classes, and here we have information on the number of chain nodes, the number of validation nodes, and the number of test nodes. I have set some hyperparameters that will be used in the model later. So later we'll go through this again. Before we dive into the structure of Graph Attention Network, we will be reviewing the 3 types of graph convolution layers that I have been working on so far. So first is Graph Convolution Network. In this graph convolution layer, the update equation for the node features is a linear transformation of the weighted average of the neighbor nodes, and here the weight of the neighbor node j is equal to 1 over the square root of degree I degree j. In GraphSage, we will take into account both the features of the node I itself and its neighbor nodes. Note that in GCN, in this sum, we do not include the features of the node I. So we lost some kind of information about the feature of the node I itself. GraphSage take into account of the features of the node I. Graph Attention Network is an upgraded version of both GCN and GraphSage. So here not only Graph Attention Network take into account the features of the node I together with its neighbors, it also takes into account into studying the relation between node I and its neighbor in order to produce the attention coefficient alpha ij. So if we look at these equations here, we can see that the node I features is updated to be a linear transformation on a weighted average on its neighbor nodes, where the coefficient alpha ij here are called attention coefficients, which indicate the relation between node I and node j. And alpha ij is computed to be softmax of unnormalized attention coefficient eij, where eij here is the leaky root of A transpose times the concatenations of WHI and WHJ. So in this equation, I call alpha ij the normalized attention coefficient and eij the unnormalized attention coefficient of the HEIJ. So before we dive into how to write this equation from the scratch, I would like to guide you through the basic step in order to write update equation in DGL. So in DGL, to simultaneously update all the node features, we basically go through 3 steps. The first step is to implement the message function, where in this implementation, we will create a dictionary that stores all the information that is needed to implement the update equation. In this case, the update equation is this equation, and in the message function, we will need to store the information that is needed to compute alpha ij, and that information will be eij. So our message function in this case basically compute eij. The second step is to implement the update equations. So we will use what we store in the message function in order to implement the update equation. So this is done via calling the reduce function. The third step here is to call the update all, where it takes 2 parameters. One is a message function and the other is reduce functions. So this step basically is simultaneously perform both the message function and the reduce function through the whole graph. Well, note that in this case, we have the parameters eij, which indicate the relation between node I and node j along any edge ij. So we will need another equation which is called apply edge function in order to store the relation between node I and node J. Well, so here is the flow of creating a single head graph attention layer. For a graph attention layer, we can have multiple heads, but the case of multiple heads is simply a stack of multiple single heads. So as long as we can implement a single head layer, then implementing a multiple head layer will be trivial. So here, let me just turn off the camera so we can go through the nodes. Here is the flow in writing a single head graph attention layer from the scratch. First, we will apply a linear projection to all nodes via the matrix W. And second, we compute the attention coefficient Eij, the unnormalized attention coefficient Eij, which appear in this equation, the equation number 3. And the third step is to write the message function, the reduce function, and send information through H and update the node features via the update all functions. For the initializations, we will need to initialize the matrix W and the attention parameters A. So if you look at this equation here, there are two learnable parameters, which are the matrix W and the attention parameter A. W take in the in dimensions, and it gives the out dimensions. The attention parameter A here take in twice of the out dimension. Here, if you look at this equation, you can see that because we concatenate WHI and WHJ, that will increase the in dimension to 2 times. So the in dimension for A will be twice of the out dimensions. And the out dimension for A is 1. We set, in both cases, we set the bias to false. Whenever we initialize these parameters, we also reset them so that we will initialize these parameters by the Xavier normal with ReLU gain. So this just follows the official documentation on the initialization method for these parameters. So in this reset parameter function, we initialize the linear projection or the matrix W together with the attention parameter A by the Xavier normal initialization with ReLU gain. And first, we will be writing the equation number 3, where this is an user, the H attention function here is an user-defined function for this equation, and we want to return a dictionary where the key is E, which indicate H, and the value are the values Eij, which just indicate the relation between node I and node J. Well, in this equation, we can see that we need to concatenate WHI and WHJ and then apply the attention parameters. So this is exactly what we are doing here. We will concatenate the features WHI and WHJ. For each of our node, we will create a features called WH, that is W times the node features. So we concatenate these two and we apply the attention parameters. And after that, we apply the leaky ReLU function and return a dictionaries. So note that this dictionary will be stored in h.data via g.applyH. This function could be implemented later. And now we will be implementing the message functions. As mentioned before, the message function will store all the informations that are needed to do the update equations. And if we look at the update equation over here, in order to implement this update equation, we need two things. First, we need the attention coefficient alpha ij, and second, we need all the features hj. So here, because we already have Eij via the H attention functions, so we can simply code it here. So note that these features, this value E are stored in g.applyH are stored in h.data. So for E, we simply call h.data, and for WH, this is already initialized at the beginning of our forward module, which we will see later. So we simply call h.source WH. And here is the update equations. So note that at this point, we already have all the node Hj, all the features of the node J, which are Hj stored in WH here. We also have Eij, which are stored in E. So the only thing that is left to compute this equation is to compute alpha ij equal to the softmax of the Eik, where k is in the neighbor of I at the position j, and multiply this with Hj. So if we go down here, this is the update equation, which is implemented by the reduce functions. So the reduce function always take in the nodes as the parameters. Here first we will compute the attention coefficient by calling the softmax functions on the unnormalized coefficient Eij along the feature dimensions, and then we will take a weighted sum of the neighbors by where the weight here is exactly the alpha ij. So we simply use dot sum of this weighted sum with the weight equal to alpha, and we sum over the feature dimensions. So this dimension indicates that we sum over all the neighbors of the node I. And here we will return a dictionary which contains the new node features. And the forward function here simply combine everything that we write before. We have G and we have H. H here is usually initialized to be the node features, the initial node features. So first we will store all the initial node features via the keyword H. We will apply the linear projection into the node features, and we will assign these new feature values into the keyword WH, and we compute the tensions Eij to all the H via the function H attention that we write above, and by calling g.applyH, we just assign Eij to all the H of the graph. And then we will use update all on the message function and the reduce function in order to send information through all the H and update all the node features. And at the end here, we will return the new node features. So note that the new node feature here would have dimension equal to the out dimension. Well, let me just run this code, block of code. And here I would like to have a sanity check to see whether the data can flow through this graph attention layer. So we call the graph attention layer on in dimension equal to 1433, and out dimension is equal to 7, which is the number of classes in our case. So the input is the graph, the Cora graph dataset, the graph G, and to call the features, the node features, we call g.nData fit. So here we can see that the output has shape 2708, and 7 is the number of classes. So the layer here work correctly. And next we are going to combine multiple of these layers so that we can form the multiple head graph attention layers. So in the initializations, we take in the in dimensions, the out dimension, and the number of heads. We will initialize the number of heads to number of heads. And here I want to go back to the hyperparameters that I set in the beginning. So here I set the number of heads to 2, the hidden dimension to 16. So hidden dimension will be used when we create the model later. Let's look at the multiple head graph attention layers. So here we have note that in this case we have two heads, and I set self.heads here. This is a collection of single head graph attention layer, and in the forward pass I simply compute the output for each of the single heads here and then concatenate them. So in this way the output dimension will be equal to the out dimensions times the number of heads. Well, let's say I have n nodes, then this will be the dimension for the output. Let's have a sanity check, right? So here let's call this module and flow the data through it. So if everything is correct, we should have shape which look like this. Actually, I already run this code. So the shape should be the number of nodes equal to 2708. The out dimension will be output dimension originally equal to 7. Number of heads is set to 2. So this is 2708 times 14. Well, maybe it's better if I clear the output and maybe don't display these numbers. Let me clear the output and rerun everything. Okay, we are here. So now we are ready to write our model. So we have a very simple model where we feed in the input. We create the first multi-head graph attention layer. We apply the elu function to the output, and we will feed through the second multi-head graph attention layer, and we get the output. So in the initializations here, we only need to initialize these two multi-head graph attention layers. For the first graph attention layers, well, the output here, maybe let me just write, the output will be n times number of heads times the hidden dimensions. So here, the hidden dimensions is the output of the first graph attention layers. But because we have multiple heads, so the output will be number of heads times the hidden dimensions. So this will be also the input for the second layer. So this is the input for the second layer, and because we want the output dimension to be equal to outdim, so we set output dimension to equal to outdim, and for the second layer we set the number of heads to be 1, so that the out dimension could be outdim times 1 equal to outdim. So here we have n and outdim. For the forward, it is quite straightforward. First, we feed through the first attention layer, and then we apply elu, feed through the second graph attention layer, and then get the output. Now we have the model, we have the data, we are ready to write the chain loop. So here is the train function for one single epoch. So we take in the model, the graph, the loss function, and the optimizer. First, we put the model to the chain mode. We extract the features of the nodes, and we extract the labels of the node. We zero grad the optimizers. We feed the data through the model to obtain the output logits. So here we simply feed the graph and the features through the model to obtain the output logits. In the training, we only consider the chain mask. So we only consider the logits on the chain mask. So our loss will be the loss which take in the logits on the chain mask, and the labels here will also be the label on the chain mask. Note that in this case, we are having multi-class classification problems. So later we will initialize the loss to be across entropy functions. We do loss backward, and then we do optimizer step. Here we will compute accuracy for the chain mask. So prediction will be the position in which we have the highest value for the logits. So that's why we do up max here. And accuracy will be comparison between the prediction and the label, and we take the mean of that comparisons. So in the chain function, we will return both the loss and the accuracy. Now go to the validation functions or the evaluation function that I call. We also take in the model, the graph, the loss functions, and the optimizers. In fact, the optimizer here is redundant. So we first put the model to evaluation mode. We extract the features and the label from the graph. We forward to get the predictions. And here we compute the loss on the validation data set, that is the validation mask. So the loss function here is computed on the validation data set. And then we get the predictions by taking the position with highest value, and we get the accuracy by comparing the prediction with the labels. So we also return the loss and the accuracy. In the training, here I just set a manual seed for reproducibility. I set the number of epochs to 40. So here we initialize the model, and note that we set in dimensions. We have in dimension equal to 1433. We set hidden dimension to 17. Our dimension is the number of classes, that is equal to 7. Number of heads is equal to 2. So here we will print out the number of parameters for the model in terms of million parameters. Actually, this is quite a small models. Here we'll set the loss to be cross entropy loss. The optimizer is ADMW, and the learning rate is 0.01. So here we write the chain and the test loop over 40 epochs. So for each epoch, we will run the chain loop, the test loop, and then we print out the result. And here note that because we don't need optimizer for evaluation, so this keyword should be ignored. So here is a training. As you can see, it goes quite fast. And after 40 epochs, we can see that the chain loss goes down nicely. It looks like we are already overfitting the chain data because the accuracy here doesn't get better. For the validations, it is still nice. So just now I say it overfitting, it's not correct because we can see the chain loss still go down. It doesn't go down that much, and it doesn't go down to like nearly zero, and it doesn't have the effect that the validation loss would be increasing. So at this point, everything is good. Here, if you change the number of epochs to, I want to see what happened if I change number of epochs to 100. Let's see at which point we will overfit. So here you can see that after 70 epochs, after actually 60 epochs, no, 50 epochs, the loss start to increase. So at this point, we can see that we overfit the training data. So the best number epoch that should be set should be around 50. Right? So let me just set to 50 to make things nice. All right, so that is Graph Attention Network from the scratch. If you want to use the module from DGL, so here is how it can be used. So to use Graph Attention Network in DGL, you simply import this GATConv from the GL. And here is the model using this Graph Attention Convolution from the GL. So we also have the exact same model where we have two attention layers. So we but there is a difference, slight difference in this case. So the output of this GATConv will be number of hits and hidden dimensions. Before I purposely reshape so that the output is in this form. So purposely I purposely concatenate all the output in all the single hits so that it appear in this form. But in the official implementations, they just give a collections of all the outputs produced by the single hits, so it is in this form. So from the first graph attention layer to the second layer, we need to do some reshape so that the output appear in this form, and then we can feed through the second layer. The rest would stay the same. So here we will feed the input through the first layer, and we do a reshape so that at this point, after doing the reshape, the output is in this form, and we will feed this through the second layer. So once we feed through the second layer, the output will be well, it will be number of hits in this case is 1, and out dimension. Yeah, I also write here. So here we don't want to have this number 1, so we will squeeze this dimension out so we get the desired output. So here is a sanity check. We initiate the module, and here I just print out the original shape of the node features and also print out the shape of the output. So you can see the original shape of the node feature is it has output dimension 1433, and the output shape has dimension 7. We call the train and test loop exactly as before. We just need to put in the new model, right? And here we also print out the number of parameters for the model. I set exactly the same optimizers, same learning rate, and here for our evaluation function we don't need the optimizers. So let's run this. So here you can see the loss go down, the chain loss go down, the validation loss also go down, but just now we run for 50 epochs. So let's see what happens after 50 epochs. So just nice, the validation loss go down and it doesn't overfit the training set at this point. But I guess that wouldn't be the case if we train for 100 epochs. So here we can see after exactly about 50 epochs, the validation loss start to increase, and here still the training loss go down, but that is not helpful because validation loss increase, that means our model perform worse, right? So it is very much the same situation as the previous case. The accuracy, in terms of accuracy, here we get about 75% after 50 epochs. For the model we code from the scratch, it is slightly better. We get 76%. Well, this is also the end of this tutorial. I hope that via this tutorial you have better understanding about Graph Attention Network. Thank you and see you next time.